Stereochemistry. It's the subject that deals with the 3D arrangement of molecules in space. This 3D arrangement can have a profound impact on the reactivity of the molecule and, of course, in other applications in biology, of course, in chemistry as well. So let's take a look at the classification of isomers. We already talked about some of those. We talked about that if you have, in this flow chart right here, if you have a pair of non-identical compounds, if they have different molecular formulas, that they are not the same, they're not isomers, they are different molecules. But if they have the same molecular formula, then they become isomers. But the question is, well, what kind of isomers are they? We already discussed constitutional isomers. So those have different atom connectivity, but of course the same molecular formula. Look at this one right here, with this amine. If you check the formula, it's going to have the same exact molecular formula, but look at how the atoms are connected. So you have your amine group, NH2 here, is attached to the last carbon rather than the middle. So now the most important part of all of isomers is stereoisomers. And stereoisomers can be divided into two types. But what are stereoisomers? Stereoisomers are, they have the same connectivity. Notice the difference. They don't have a different connectivity. What's different about them is they are arranged differently in space. Here's an example. So we have enantiomers. Those are non-superimposable mirror images. Of course, we will discuss this more in detail as we go, but just to give you an idea of what to look for. So the same connectivity. You cannot say that these are connected differently, but these are mirror images of each other. We call them enantiomers. They are non-superimposable. You can't take one and superimpose on the other one. You have the next one is you have diastereomers, and those are not superimposable, but they are not mirror images. So they could be like the cis and trans, as you see here. But again, these are not superimposable mirror, and they're not mirror images as well. We'll get to this toward the end. But most of our discussion will involve enantiomers. So as I said, in stereoisomers, isomers that differ only in the way atoms are oriented in space. Very well. So if you remember, we dealt with cis and trans. This is an exact example of stereoisomers. So what do you have here? You have cis and trans. Okay, let me get the pen to get working here. So again, these are on different sides. Look at the chlorine right here and look at the bromine. This is trans, but they are on the same side here, so that would be cis. So what do they have? They have the same molecular formula. So the same molecular formula, same connectivity. And of course, what they have different is they have a different arrangement of atoms in space. So again, they have a different arrangement of atoms in space. Look how the bromine and the chlorine are on opposite sides here, but they are on the same side. So that's a different arrangement of space rather than having them, both down, one is up and the other one is down. That's what we mean. So what is the name of that? Well, a particular three-dimensional arrangement is called a configuration. Okay, so make sure you don't confuse this with conformation. Conformation is when a bond rotates, a single bond rotates, and it's happening continuously at room temperature. No, this configuration does not rotate. It stays, it's like this is stationary. You won't have, this bond rotate and then the carbon is going to make now the bromine up, or this chlorine is up. That's not going to happen. So where does this idea come from? Quickly, it comes from the Greek word cher, which means hand. And it really comes from the hand. Your hands have mirror images of each other, your left hand and your right hand. You can take them right now and you can try to simply compare them. And if you compare them, you're going to say, okay, let me see if I can superimpose them. You can do whatever you want with your hands, but it has to be thumb over thumb, palm over palm, and they have to superimpose. You can't just take, your hand and just say, okay, like a clapping. No, that's not superimposing, because your palms now are facing different sides, right, or different directions. So you can do whatever you want. They're not going to superimpose. So these are mirror images of each other, left hand and right hand. Look at the mirror in the middle, right here, but they cannot superimpose. We want to keep in mind this idea of that they cannot superimpose. So that's what we call a chiral object. A molecule, just like the hands, can be chiral if it cannot be superimposed. Superimposed. Just like if you ever, say, okay, what does that mean, superimposed? Just remember the hands, that they cannot be superimposed on top of each other. Think about gloves. That's why you have different gloves, one for each hand. Shoes. So there are many chiral objects, right, in nature. But again, they cannot superimpose. So a chiral object, a chiral compound will have a pair of enantiomers. This is a key word right here, what we say enantiomers. And most importantly is that the reason why it's a chiral is because it does not have a plane of symmetry. So a plane of symmetry means they cannot cut. You cannot cut across, and you're going to have two equal sides. But let's look at this. Imagine this is right here. Imagine you have two molecules. And if you have a model, you can really do this and you'll see it. We'll do this when we meet next time. I might put a video or two in here just for you to see how they cannot superimpose. But if you look at them, these are mirror images. They are mirror images. But the question is, do they superimpose? So these mirror images, the key here is that they are not superimposable. They are not, that's the key word, superimposable. What do I mean by that? Okay, take one, kind of like rotate the other one, try to superimpose it. You will have now the green here facing the back. The blue and the one on the top here are going to align, but these two are going to be on the opposite directions. So they are not superimposable. And of course, these are what we call a pair of enantiomers. And of course, each is chiral. So again, chiral means it's not mirror images that are not superimposable. So what is meant by a carbon that, so let's give an example because we need an example here. How do we know, how do we begin to know whether a molecule is chiral or not? And it has enantiomers. So take a look at these atoms. If you look at these atoms, they are different. They don't have to be atoms. They can be groups or substituents. If you notice that one criteria is that they have to be all different. You have to have 4 different groups. Count them here. You'll see that these are different colors, which again mean that they are different groups. So again, those are different groups. They could be atoms. All right, so let's take a look at how we would actually see that. Very well. Imagine you have this formula. Let's just do a structure right like this because we will show you how to draw them in 3-dimensional soon. Okay, so just showing you, of course, we're going to use that. Now, take a look very close. Look at a carbon, right, that is bonded to 4 different groups. It's called a tetrahedral stereogenic center. A stereogenic center, or a chiral center, an asymmetric carbon. This is the first criteria for having a chiral molecule. So, and most chiral molecules contain 1 or more stereogenic centers. So let's take a look. Look at this carbon. Does it have 4 different groups attached to it? No, it has 3 H's. Right away, you know those are not 4 different groups. You can take a look at these. This carbon. Nope, it has 2 H's. Even though on the sides, it has different groups. It has to be 4 different groups. Even this one. The only one that matches or satisfies this criteria is this one right there. So we put a star next to it. So let me show you the 4 different groups. You have bromine, you have the methyl, you have the chlorine, and of course you have the ethyl. So notice how it has 4 different groups. So keep that in mind. This has to be known as well as you know your name, really. 4 different groups. 4 different groups. Now, a molecule is superimposable on its mirror image, and this is said to be achiral. So achiral is basically the opposite. It has a mirror image, but it's what? Superimposable, meaning you can take one and place it exactly on top of the other one, and it's going to align perfectly. So one of the, like an achiral molecule would be something, and I'm going to use a shorthand here, is something like, you have a CH3, of course, a CH3. Even if we have a Cl and a CH2, CH3. So none of these carbons have 4 different groups. All of them have at least 2 of the same groups. Like this one has 2 H's, this one has 3 H's, this one has 3 H's, and this one, can you see if it has 4 different groups? So this one is different, that one is different, but guess what? These 2 are the same. So so we know 4 different groups. So therefore, it's achiral. Now it has a plane of symmetry. You may not be able to see it, but we need help of models down here. So bear with me here. What do I have here? I have butane. I have butane, so that's CH3, CH2, CH2, and CH3. You can trace them right here. So none of these carbons, go ahead and inspect them. Does each carbon have 4 different groups? None. And here it is. What do I mean by that? It has a plane of symmetry. So this would be achiral. But let's look at the plane of symmetry. So the plane of symmetry is, again, having 2 equal sides, having 2 equal sides. Do you see? So this is, if you remember, the anti-conformer for butane, and this is from the front view. If you take a look here, there's a plane of symmetry, and I'm going to try to use color here so you can see it, that cuts right in the middle, cuts right in the middle. And I'm going to post videos from YouTube to show you help. I don't have the capability with the cameras. Okay, I'm not sure if you see it, but I tried to trace it. Here, I'm going to cut in the middle so you can see it. Okay, not the best. It's hard to draw a straight line using this writing pad for some reason, because it just loses. Okay. Okay, so do your best. So you see how this side is the same as the other side. So you see the plane of symmetry. Which is this one right here. Where is your plane of symmetry here? By looking at it in 2 different representations. Remember, this is a very crucial skill in this class, is for you to be able to really juggle between two of these representations. Simply translate between this one and that one. So basically, this is a front view. If you were to look at it, this is the anti, I mean. This would be the plane right here. So it's symmetrical and right here. So that's the plane of the molecule. There's symmetry. You can even draw this once again. Let me see with this writing pad if I can do it here, but it would be basically right here. Okay, it's not the best picture. I admit this. Let me here see if I can fix this one at least for a little bit here. But if you can see it, right here. So you see the plane of symmetry right there, cutting across. Again, this would be achiral. This would be achiral. Now, let's look at what we did down here. Okay, what we did down here is we simply switched one of the one of the atoms to a chlorine. Look down here. You see it right here, right here. So this is now 2-chlorobutane. 2-chlorobutane. If you notice, this one now does not have a plane of symmetry, at least at this carbon. There are two things that are happening at this carbon, is that you change, again, you have 4 different groups. So here's 1, here's 2, here's 3, and there's 4 different groups on this carbon. So you have a chiral carbon right there. So again, a chiral carbon, or what we call a stereogenic center. And if you look here, there's no plane of symmetry between them. You can put a mirror in between. There's no plane of symmetry between them, even if it rotates, even this bond rotates. So you see how it disappeared? How would we show that on models? So one way is, let's make this chlorine, this one right there. Let's say now this turns into blue. Right here. That's your Cl. There's no plane of symmetry. If you see it, I cannot see it. There's no plane of symmetry. This side does not match the other side. Or if you do it this way. So there's no plane of symmetry. And now this becomes a chiral molecule. And of course, this one would be achiral. Lastly, I know this is a longer video, but it's important that we explain as much as we can. The importance of this is very, very shown here, as is shown, it's very visible and apparent. Our noses can distinguish enantiomers very easily. So you can actually see that if you have these 2 enantiomers, which are mirror images of each other, so you have, in this case, you have 2 enantiomers of each other. And if you take a look at these, you'll notice that this one right here, we'll talk about this later. What does this minus and the plus mean? This would actually be spearmint oil. And this one is actually from caraway seeds. The only difference is the arrangement of atoms here. They're mirror images, but they are not superimposable. Ibuprofen. By the way, receptor sites for the sense of smell are chiral, just as active sites in most enzymes are chiral. You will see in the article that I posted, read it, you'll see how this has a profound effect on the efficacy of drugs. So you have the S isomer of ibuprofen and you have the R isomer. This one has the anti-inflammatory effects. This one has no anti-inflammatory effect. Or not anti-inflammatory. Let's just make it. Not anti-inflammatory. This one is anti-inflammatory. Thalidomide is a very, very sad case. You may want to read about it. I'll mention it when we meet. One of them is given for morning sickness for pregnant women, and then what happens is that it helps them with morning sickness, anti-nausea. However, but the S enantiomer is a teratogen, meaning it causes birth defects. You may just Google this and see the enormous damage and suffering that caused back in the 50s. Very well. So in the next video, we'll talk more about how to draw a pair of enantiomers and again, move closer to, again, a good understanding of chirality.